Thank you very much. Well, now for something completely different, as they say. Earlier on this morning, you heard a commercial by Professor Gross, commercial for quantum mechanics. I think he must have, at some point in his career, done some selling of encyclopedias or used cars. But anyway, towards the end, he admitted that there were some things which were not yet very well understood. And I think what I'm about to say may help to fill in these gaps. No, is that? Yes. Okay. You'll notice incidentally that of this great list of things which quantum theory could do very well, biology wasn't one of them. And in fact, there are problems with biology. Around about 1990, I had a paper in the journal Foundations of Physics, which called Limitations to the Universality of Quantum Mechanics. And nobody has yet said there's anything wrong with the argument. But my premise anyway is that physics is based on mathematical descriptions, and these are themselves limited. One problem is that the usual approach involves some equation for time variation, and that implies that you take a snapshot of the system at some very precise time, and you then use some mathematics to follow it forwards. Well, on the other hand, if there are these fluctuations, which are in fact infinite and have to be fiddled away, then taking a snapshot is meaningless. And in fact has led to a series of problems. So there's an alternative point of view I'm going to talk about, which perhaps one should associate mainly with the ideas of John Wheeler, which I'll talk about in a moment. But the approach I've taken has been influenced by collaborator Alexa Yardley, who's written up something called circular theory, and I've been largely putting this into more rigorous form. But first of all, well, the question anyway is whether we should ground physics on mathematics, which is the usual assumption in physics, or something which one might call creative observation, which I'll come to in a moment. It was Wheeler who introduced the idea of creative observation. Now, let me just say what problems the mathematical path has run into. Let me see if I can get this pointer to work. I don't see anything happening. Anyway. Oh, okay, right. Oh, right. Oh, thanks. Okay, well, this started off, the mathematical enterprise, you could say, started off with Newton, his mechanics laws, mathematical laws, which described all sorts of things like the planetary orbits. Then Maxwell did the same for electromagnetism. That, however, wasn't entirely satisfactory and had to be replaced by quantum theory about 100 years ago. Then this was boosted by quantum electrodynamics, which took the fields into consideration. Then the Standard Model, which worked quite well with many, describing a large number of particles. Now, the problem was integrating that with gravity, because this started not being finitely renormalizable. But people did fix this eventually. There was a multi-dimensional fix with things like strings and supersymmetry. However, then the mathematics started to get disconnected from the physics. Elegant mathematics and this dreaming of a final theory, but that didn't quite work out the way people expected. And one problem David Gross didn't mention is that there are an infinite number of, well, not infinite, 10 to the 520 different universes you get by folding up your extra dimensions in different ways. So there's a bit of a problem there, quite apart from the question of how do you mathematize biology and so on, which I won't go into here. Okay, well, then around about 1990, John Wheeler wrote this amazing article, Law Without Law. If you can find it with a search with Wheeler, Law Without Law, and download it. Now, what I have on this page is a synthesis of a number of remarks made in that paper. He said, the scope of physics is greater than we once realized. If the elementary quantum process is an act of creation, as I'll come to in a moment, is an act of any other kind required to bring into existence all that is, including the universe. If the views we are exploring here are correct, one principle, observer participancy, suffices to build everything. So, quite a dramatic claim. So let me say what his idea was. Well, it was based on quantum observation. The theory of observation is part of quantum mechanics, and says we, to every observation, there's a certain observable, and we collapse the wave function into an eigenstate of that observable. So this is a kind of intervention in the world when we observe it. And it's something that can't be reduced to passive observation roughly because different kinds of observations do different kinds of things to a system. And so a classic example is if you have a beam of particles and you have a detector which observes where that particle is, then suddenly the beam collapses it into a point. Whereas if instead you do some another observation like an interference experiment, that cannot be explained as a point particle but only as a wave. So there's something strange there. You sort of suddenly put a constraint on the system when you observe it. So he thought perhaps that's all you needed to explain everything, but he didn't have a well-defined theory to explain that. In fact, to get anywhere with this, you have to think in terms of organized observation. A disorganized observation is not going to do anything like create some special kind of system. In fact, Hameroff and Penrose introduced the idea of orchestrated collapse. They had the brain doing it, whereas Henry Stapp had the idea that mind is not contained within quantum mechanics, and mind can do various interesting things. So, right, in the next slide, sorry I didn't switch to that slide, but anyway, next slide I have the quotes of Hameroff and Penrose first of all. A network of microtubules can tune itself appropriately to achieve control of its own state of superposition and reduction. Henry Stapp had a much more esoteric idea. The conscious act is represented physically by the selection of a new top-level code, which then automatically exercises top-level control over the flow of neutral excitations in the brain through action of the laws of nature, etc., etc. And the unity of conscious thought, he thought, came into it, selecting a single code. So he has a more information theoretic approach. Now I think this needs to be extended a little further, but let me go through the sequence, as it were. Traditional quantum mechanical observation deals with an isolated measurement and specified measurement or instrument. Now we have technical devices which exert more control on nature, and they're using an organized set of measurements, and they are interactive. So any kind of gadget we have which like a a robot controlling something that's making a lot of observations, is using these measurements in an organized sort of way. But those are not natural phenomena. So I turn now to biology and talk about biological systems which do things like being adaptive. Also, what's very important, biological systems can aggregate together and join in activity. This aggregation is very important in the theory I'm talking about. They may also use of representations and use information. Okay, now this is at the moment a qualitative theory. I'll later on be describing two more rigorous things we've done, though not applied to this specific theory, but I'm going to introduce a kind of metaphor, which interestingly enough links to string theory. And this metaphor, oh hang on, that's not, let me just have a look. No, so I haven't got to the dance metaphor yet. Okay, I talked about systems self-organizing themselves to do things, and I realized when I produced this slide title, Organization Through Activity, that it was very similar to Prigoghine's order through fluctuations. Prigogine noted that when you get far from equilibrium, or in a fluctuation, you tended to get interesting kinds of organization. And biological systems are doing the same kind of thing. They organize themselves through doing things. If, say, you learn to walk, then an organized structure gradually forms. And the way this does basically is that you add new possibilities, and if the new possibilities support that action, you join them to your system, and you ignore something you do which doesn't fit in with that activity. So in fact, biological systems naturally do this business of creating a unit which performs particular actions. So this is the kind of thing which we want to put into our model as being something fundamental. So systems engage or disengage from actions as skills develop, so you get organized collections. An example of an organized collection where various models are flocking birds, and a student of mine did a similar thing through learning a skill of balance. And you might say roughly that the activity is a kind of reference frame to decide what should join in, and you produce a kind of condensate. But this is a different kind of system to the physical condensate, where you condense lots of versions of the same. In biology, you collect together things which cooperate together. So now I'm going to make my grand assumption that there is a biological phase of reality where, roughly speaking, biological things happen. Now, one way to envisage this is to say that it's something on the border between two regimes that physicists think about. Say a collection of gas particles where these move in a pretty random way, that's one extreme, and the solid where you have a rigid structure is a different kind of situation. In between, you can have a system where there's constraints combined with movement, and this seems to be the key thing. So the idea roughly is that a thing which we haven't yet studied very much in physics, well, there's a field of study called order of chaos which studies some of this, but I think is missing out the biological aspect. So you imagine things are moving about and they form groups and they disintegrate. And that's the kind of situation which is really a new situation with potentially new physics. Now I have a video, no, I haven't yet got to a video. You can think of it in terms of a dance, if you like. That's people moving in a way that's constrained by the fact that they mustn't collide into each other. Some dances have this feature of joining together and splitting up, complicated choreography. Subgroups form that exhibit organized movements. And Yardley's theory proposes two things circling around each other. But also you might see David Gross's video of a moving string as being a kind of dance. Just to show you this business of, let's see if this is going to work. Yes, good. I was going to turn off the sound. There was raucous movement in the background. These are Chinese motorbikes going around in organized patterns. It's just about a miniature. They change their form, and then a new object is introduced into the system. You'll see in a moment. They got up to 4, but I'm only going to show you 3 of them. Right, here we are, the third. This becomes a 3-body system. And you have to find a new way in which the systems can move together. And they start off in a simple circling mode, but then it becomes more complicated. Right there. It said I introduced the odd jump in editing. So here there's a more complicated regime. So, right, I'll go on to the next slide. Well, this illustrates the kind of new physics which I'm proposing. Coordinated action. There's also resonance. There wasn't really resonance in that illustration, but you can have two systems each oscillating, and sometimes they lock into resonance. So this is a new kind of thing that can happen, which is interesting because it means that it's both 2 systems and 1. You can picture systems as being a unit with particular joint behavior, but in some situations it's a useful model to think of separate systems. So in Yardley's theory, you get groups forming and reforming. And now the point is that this kind of thing can evolve. It will evolve if some systems have survived better than others or have greater value than others. If this biological aspect develops, and I'll say a little bit about how it develops in a moment. So really we're talking about new phenomena and a new perspective in things which when people have done a lot more work on it, should give rise to new physics. And this, I believe, is what will fill the gap that David talked about this morning. Then it's worth considering. It's a new concept. And doesn't really have anything artificial in it, like extra dimensions. It's just a thing that happens naturally when you have things that are moving, the movements are constrained, and units form and can dissolve. Well, now, the critical thing which makes biology different is evolution. More and more advanced structures appear through evolution as various complexes form. And I just thought of a nice example of this. Particular patterns forming is a chess game where you could say it's a kind of dance of the pieces, but particular forms like the pin and the fork have survival value. Similarly, in this biological world, particular patterns have survival value, things like feeding and reproduction. Those are natural things that happen in the biological realm. So what I'm proposing is that there are units which can form, as they form and reform, will become more complicated forms, and eventually will be the explanation for physics. We'll get back to physics eventually. This isn't just biology. So, now, we usually think of life as being something with a lot of complicated apparatus, DNA, molecules with specific properties, and so on. What I'm proposing is that this, at some level beyond the standards model, say, we have something similar happen, a subtle biosphere. So this raises the question of what is actually needed to get biology underway. And it's, in a way, it's like something lighting a fire. If biology can get going, then you can get these more and more complicated forms. And I believe that's all needed. All that's needed basically is structures forming and dissolving, and a code, and a supportive environment. One thing that's equivalent to DNA is, well, you can think of DNA as being mutual templates. One of the strands is a template in which you form the complementary strand, then they split up. The complementary strand is then a template on which the first strand can form again. In other words, you don't really need very much to get replication. There just need to be these complementary structures will provide one mechanism for it. And then you get cumulative development, as rather happens with software. And now here's an idea as to what how you might get more and more complicated things developing. Well, first of all, signals. A signal is basically something which can connect with something else. So that's a simple one structure, well, two structures interacting that allows signals, and that includes semantics, what a signal means, syntax and language systems. Well, that's one development where things can get complex. And the philosopher Suzanne Langer noted that symbols can work in two ways. One is more associated with science, where you use symbols to refer to something, whereas in art you have symbols which have particular effects. And I'll get into this because one of the things you get from this which you don't get in conventional approach is music. Well, okay, you can combine symbols to make propositions, so the idea of things being true and false occurs. From that, there's logic, which is the relationship between propositions. Then you can go to formal systems and mathematics, then things which satisfy mathematical laws, and universes, and these universes can contain matter and life. So I'm fairly sure each of these steps could be studied with models. We did a model with one simple thing. So the idea is you find a system which can do something like deal with propositions, and then some combination of such systems might be able to do something useful like logic, which will be selected out. So just this making more complicated systems with selection of those which are useful is going to give you in principle mathematics. And then you say what actually happens in culture is you develop mathematics, and then mathematical models to describe the surroundings, and then you can get to the work of designing things, and you design things on the basis of mathematical laws. And the universe is just a technology, you could call it, based on this subtle life. And this, incidentally, will account for the universe being supportive of life, because naturally this subtle life is going to make things which have value to it, and presumably some forms of life could have value. So this is a bit like the Penrose triangle. I think in one of his books, Shadows of the Mind, I believe it's the end of the book, where he notes physical systems. Mind is based on physical systems, and mathematics originates mathematics, and physics obeys mathematical laws. Well, he didn't quite have that right, because Hameroff and Penrose thought that the only kind of mind you can get is the brain, whereas one can perfectly well have these biological developments in more subtle systems. So locating mind initially in the subtle biosphere clarifies the Penrose triangle idea. In fact, Wheeler's article assumes that the universe starts off as something which doesn't have life, but then it has observers, and observers can then work away shaping the universe. So this is a bit essentially the same kind of idea. Okay, so I say this is the real M theory and may help to take us beyond where we are now. And now a little bit of controversy before I close. Well, I won't go into that. I'll just mention space and music. Well, as in the modern approach, space is not something fixed. It may change dimensions and so on. So if we have an observer which can look at space, it can do some shaping on it. And so the idea is we don't get from to our universe by some arbitrary folding up mechanism, but it's an organized process with a mind that went before space. Music, well, let me simply say that there are various things which I believe cannot properly be explained in terms of regular theory. I did a collaboration with a musicologist, Tethys Carpenter. You can find our paper on our web pages if you follow the publications list. A quote from our paper is, "Conventional theories do not account for the specificity, complexity, functionality, and apparent arbitrariness of musical structures. Psychologists who say this is what goes on in music do not explain things like that." But the kind of explanations we have been talking about will fit in with that. That's because a code which can be functional. Now, I said we have some things along these lines. It's a paper by myself and Hermann Hauser called Multi-Stage Acquisition of Intelligent Behavior that explained the logic of development in terms of a picture like this. And George Osborne did a thesis on cognitive mechanisms of guiding psychological development, and this was an actual computer program which took structures and assembled them, observed the way these structures behaved, and was able to begin cognitive developments, and that was going nicely until the powers that be declared that he couldn't go on with this if he wanted to continue as a student. Weird business. Templates, well, this is a concept which is useful for explaining how things develop. Your simple structures act to organize complicated behavior. So I think this is the real M theory. Now I'm getting on to the more controversial bit. Back in 1987, I wrote a paper for the journal Physics Education, where I proposed that eventually physics and spirituality would be unified. As you'll see, it's quite similar to this, but it's taken quite a time to put that into to clarify what was going on. That there'd be the subtle level, and then I said this would actually connect with religion, so scientists might have problems with this. There are various things, Eastern philosophy, which was really my starting point, that mind is the basis of everything. I read a book by theologian Keith Ward, which actually explained creation in terms that matched very well the view that I was getting from my own approach. Then there's intelligent design. Now that's very strange and political, because to be a scientist you have to take as an axiom that intelligent design is wrong and expend all your efforts on one side. Now, in fact, admittedly, the creationist people are interested in this, but they made the decision to see what could be got from science. And intelligent design is, in fact, an entirely scientific enterprise. Stephen Meyer is a philosopher with an impeccable pedigree, namely a PhD from Cambridge. He's written this book, Signature in the Cell, which discusses the science. He's saying how cells have a remarkably complicated structure, and it's hard to see how these could be produced. Whereas on my picture, the subtle level is able to experiment with designs and get better and better ones. It's not constrained by the universe. Now I see that my time is almost done, which is good, because this last slide is the end. I'm the sheep that are separated from the other sheep, as shown in this painting by my wife. Thank you very much. Yeah.